So let's do orthogonal projection. Before we can start, we need to be comfortable with some basic rules. If two vectors are collinear, for example, vector u and vector v, then we can express one as the scalar multiple of the other. For example, u here is k times bigger than v. K is a scalar that we're multiplying to vector v, which will scale up this vector and give us vector u. So when two vectors are collinear, such as this, we can express the first one as a multiple of the second. Another thing we have to know is that if two vectors are orthogonal, perpendicular, right, 90 degrees, then their scalar product gives 0. So here's, let's say, vector A, and let's say here's vector B. They're 90 degrees with respect to each other. Then A scalar product B has to give us 0, because magnitude of A times magnitude of B times cosine of 90 degrees. Cosine of 90 degrees is just 0. So this goes away, this becomes 0. And then 0 times these two gives you 0. And this, by the way, is the geometric definition of the scalar product. Finally, the scalar product of a vector with itself is the square of the magnitude of that vector. So let's say we have vector v, and we're taking the scalar product of that with itself. And what we get is magnitude of v times magnitude of b times cosine of the angle between them, but the angle between them is 0 degrees. And cosine of 0, this part here, is 1. So what we have is magnitude of v times magnitude of v times 1, and that's just magnitude of v squared. So here we have vector A, here we have vector B, and let's try to find the orthogonal projection of A onto B. So what that means is we're going to have to drop down this perpendicular line from the tip of A onto B. So this is 90 degrees here. The vector that's formed here on B, what we can call the shadow of A onto B, from here to here. This I'll label P because that's the projection, the vector. And we notice that vector P and vector B are collinear. So that means P, vector P, is a scale multiple of B. In fact, it's been shrunk by a certain factor, which we call K. Also, since vector A and vector P are both originating from the same point, then when we connect the head of A and the head of P together, what we get here is vector A minus vector P, which is itself a vector. Now this vector, A minus P, is 90 degrees to vector B. So if we take their scalar product, A minus P, scalar product with B, we know this should give us 0. Now if I replace vector P with K times B, what I have in the brackets is A minus K times B, scalar product with B. And that's 0. Now I can distribute B inside the bracket. I can FOIL it in. That gives me A dot product with B minus KB dot B, and that's still 0. Now if I bring the negative KB dot B to the other side, I get A dot B equals K times b dot b. But we remember that b dot b is really just the magnitude of b squared. So now dividing both sides by the magnitude of b squared, we can solve for k, and that gives us k equals a dot b divided by the magnitude of b squared. Now we've just found the value of k. This is a number, this is a scalar, and it's the number that when we multiply this b up here, it will give us the value of p. It will give us vector p. So p, vector p, is really just a dot b divided by magnitude of b squared times the vector b. That's how we find the projection of A onto B.